Let's just jump right into it. Today, we are decoding a paper that, honestly, completely blew my mind. We're looking at H.B. Barlow's 1961 work, Possible Principles Underlying the Transformations of Sensory Messages, and our entire goal in this explainer is to solve a mystery. What are our sensory nerves actually doing when they process the world around us?
To kick things off, Barlow uses this really striking analogy. Imagine, for a second, that you had no idea birds could fly. You'd never seen it? If you were handed a bird's wing, what would you think it's for? I mean, you could study the smooth feathers, the prominent bones, the powerful muscles all day long. But without knowing its aerodynamic purpose, without knowing about flight, that wing is just a complete, unsolvable mystery.
And that brilliantly captures Barlow's core argument. On one hand, we have biological observations, right? The feathers of a wing, or, the physical anatomy of an eye. But to truly understand them, we absolutely need physical models. For the bird, the model is aerodynamics. For our nervous system, Barlow argues we need a model of sensory economy. Just watching nerves fire isn't going to tell us what operations are actually happening. We have to understand the underlying purpose.
So here is our roadmap for getting there. We're going to start with the roots of sensory economy, then we'll walk through Barlow's three progressive hypotheses: the password, controlled pass characteristic, and redundancy reduction. And finally, we'll wrap up with what he calls the ultimate economy. Let's get into it.
Starting off with Section 1, Roots of Sensory Economy.
We actually need to rewind a bit to see where this whole functional perspective came from, because Barlow wasn't just operating in a vacuum here. The seeds of this idea were planted way back in the late 19th century by thinkers like Ernst Mach in 1886 and Karl Pearson in 1892. Fast forward to 1961, and Barlow basically takes their philosophical ideas and applies them directly to hard neurophysiology. Now, here's the core philosophy that sparked Barlow's thinking. Mach and Pearson argued that the concepts and laws of nature serve one main purpose: bringing order and simplicity to our complex sensory experiences. The goal is to achieve an economy of thought. So Barlow looks at this and wonders, what if the physical nerves themselves are wired to achieve this exact same economy? Like, what if they literally simplify the data before it even has a chance to reach our higher brain? To ground this idea, Barlow looked closely at the visual system of a frog. Now, frogs don't use vision the way you and I do. They don't really have complex form discrimination. Instead, their eyes are wired to trigger highly specific survival responses based purely on simple movements. And this exact observation leads us straight into Barlow's first functional theory. Which brings us to Section 2, Hypothesis 1, the password.
So this is the simplest model for what a sensory relay might actually be doing. Think of a sensory relay as a preset detector that's just waiting for a specific password. When a small moving object enters a frog's vision, it acts as a visual password that unlocks a very rigid four-step behavioral sequence: alluring, turning, hopping, and finally, snapping. The relay's only job in this scenario is to detect that specific snap-worthy password and literally ignore everything else.
Moving on to Section 3, Hypothesis 2, Controlled Pass Characteristic. Now, as we know, biology is rarely that simple. So let's step up the complexity a notch. Under this hypothesis, sensory relays aren't just rigid locks waiting for a password. Instead, they're dynamic, adaptable filters. Barlow uses the example of muscle spindles here. The nervous system can actually adjust the sensitivity of these sensory relays on the fly, kind of like turning a volume dial up or down. Higher brain centers send feedback down to the relays based on success or failure, tweaking what information actually gets passed through. It's honestly remarkably similar to early machine learning concepts.
To really cement the difference between these ideas, Barlow gives us this absolutely brilliant newspaper editor metaphor. Hypothesis 1, the password, that's like a permanent editorial policy. Say, a magazine that only publishes sports, period. Hypothesis 2, the controlled pass, is more like an editor temporarily cutting articles just because they ran out of page space. But Hypothesis 3, that introduces the ultimate editorial question. Is this news? Has it been said before? If the answer is yes, then it's redundant, and it gets cut.
And that leads us to Section 4, Hypothesis 3, Redundancy Reduction.
Okay, this hypothesis right here is the absolute centerpiece of Barlow's paper. It seamlessly bridges biology with pure information theory. But first, we gotta understand what redundancy actually means in this context. It's essentially the fraction of a communication channel's capacity that is not occupied by the actual message. Simply put, it is wasted space. If your nerves are firing just to tell your brain something it already expects or knows, that is biological wasted space.
The crucial point to remember here is that nerves have absolute physical limits. Barlow actually created a mathematical channel capacity equation for this. He treated sensory pathways exactly like communication channels, complete with discrete time intervals and limited impulse frequencies. Think about it like your home internet connection having a maximum bandwidth. Your optic nerve has a hard mathematical maximum capacity for carrying impulses.
Because of that physical limit, the nervous system has one very distinct goal: preserve the actual information but discard the redundancy. So, unlike the first two hypotheses, which basically just throw data away, this method neatly packs messages into smaller channels. It economizes nerve impulses so we use as few as possible on average, but without losing any of the actual news.
Let's look at how Barlow visualized this recoding process, because it's super cool. He compares incoming sensory impulses to developing a photographic negative. If you take a really long time exposure photo, the constant background turns into this uniform gray, right? It just fades away. But anything that changes, anything unexpected, stands out sharply. Our sensory relays do exactly this. They silence the constant expected background noise, and they only fire nerve impulses for the unusual and the unexpected.
By economizing these impulses, the brain is naturally building an internal model of its environment. It stores the relative frequencies of past sensory inputs. It allots almost zero impulses to the things it expects to happen and reserves massive bursts of impulses for the unexpected. And why does this matter? Well, because it massively curtails the search effort required for learning. If a rat is navigating a maze, its brain doesn't have to constantly process the texture of the floor. It only needs to process the sudden appearance of a piece of cheese or, a predator.
Finally, we reach Section 5, the ultimate economy.
Barlow follows this redundancy reduction theory to its absolute, mind-bending conclusion. Because your brain has vastly more neurons in the cortex than in the incoming sensory pathways, the channel capacity actually expands as you go up. Combined with redundancy reduction, Barlow calculated that the aggregate number of impulses required to carry information drops enormously. In fact, he speculated that incredibly complex sensory situations could potentially be distilled down to minimal activity, maybe even down to one single nerve impulse firing at the highest level of your brain.
Which leaves us with a really provocative question to wrap up this explainer. Could your entire, incredibly rich experience of the world right this very second, the screen you're looking at, the sounds you're hearing in this room, be represented by the firing of just a single, highly coded neuron in your brain? Barlow's mathematical models suggest it's entirely possible. And if that's true, well, it completely changes how we perceive the reality constructed inside our own minds. Think about that for a while. Thanks for hanging out with me today, and keep questioning what you see.